Now, if you remember, what I did actually, what I did leave off with was expected value. That was the last thing I left off with. Okay? That's actually, in other words, what I got up to. Okay, but we're going to do that today. And then what we'll probably do is start chapter 9 as well. 9 does a lot more probability. It goes a little bit more into it. So with expected value, I mean, the definition is here. It's the average gain or loss of an event if the procedure is repeated many times. The whole idea with expected value is if you were to do the experiment, the game or whatever, more and more and more times, repeat it many times, expected value is how much you expect to win or lose in the long run. We're only going to do expected value with experiments where you're either going to lose or gain money. So expected value would be how much you would gain or lose if you kept playing the game over and over again for a long time. I mean, that's how we're approaching it in this book. We're mostly going to use expected value with games like, if you draw a card and you get this, you get $1. If you don't draw this card, you lose money, that kind of thing. So we're only going to consider expected value with experiments and events where you're either losing or gaining money. At the expected value, again, expected value tells you how much you should expect to win or lose if you keep on playing the game many times. And I do have and the definition is here. It's really not that hard actually to calculate it. You just take each outcome you get, or in this case, how much money you're going to get or lose, multiply it by the probability of that outcome, and then you add up the results, add up the product. Okay, so that's how we calculate it, but we also like to interpret it. Well, if the expected value is negative, in the long run, you're going to lose money. Once in a while, you might win. Okay? Sometimes you win, not always. In the long run, you're going to lose money, though. So those kinds of games, you really don't want to play. Theoretically, at least. I mean, for all you know, the expected value might be like, I don't know, if you're gaining like a cent or like 10 cents or something, maybe something like that you might want to keep playing over and over because you're going to lose. Yeah, but you're not going to lose much. So in theory, though, you don't want to play it. And if it's positive, those kinds of games, you will gain money in the long run. It might not be much, but you will gain. Sometimes, though, you will lose. Not always, but sometimes you will. We'll do some examples today where you could lose money, but in the long run, you would gain money. And of course, and it could be possible that the expected value is 0. In that case, we say that the game is fair. In the long run, you're not going to win or lose anything, though. Those kind of games are fair. So I'm guessing casinos like the games where expected value is negative. For us, I mean. Mostly because if we play, we're going to lose money in the long run, and they're going to gain money. That's what expected value. So let's do some examples. For instance, suppose here we're at some kind of contest, a charity event or whatever, and raffle tickets, they're selling them. Each ticket is $3. Okay? Everyone is allowed to only buy one ticket. Okay, all right? And let's say 150 tickets altogether have been sold, including the winning one. The way these games are, I guess somehow they call out the ticket by either number or whatever. But whoever has the winning ticket gets $300. So the question is, what is the expected value to you of this game, of this contest, of the raffle ticket? And saying the expected value to you does actually make a difference, because you can consider expected value to who's ever running the contest, like a company, a charity, whatever. Anyway, so how would we do this? Okay, well, since we're assuming the tickets are equally likely, okay? They all look the same. You can't tell, except for the number on it. You really can't tell which is which. So the probability of someone having the winning ticket would be 1 out of 150. That's the probability of winning. There's only one winning ticket. 150 have been sold. And how much are you going to win, though, if you have the winning ticket? Well, yeah, you'll win $300, but don't forget, you had to pay $3 to get that ticket. So in the end, you would get $297. Okay, notice that I had to subtract how much I paid for the ticket. I think last time I might have gotten that, although I don't think we got up to this example. Either way, this is right what I'm doing here. Okay. Now, what would the probability of losing be? Well, 149 out of 150. Any of the other tickets is a losing ticket, so to say. Well, I don't think they call tickets losing tickets, but also you can think of it this way. If you're not going to win, you're going to lose. So winning and losing are complementary events. So you get one, to get one probability, you take the other and subtract it from one. And if we lose, we're not getting our money back, but how much we paid for the ticket, that is. So we would lose $3. Okay, so what would the expected value be? Well, that's what this is, right? We're taking each probability, we're taking each outcome, in this case, winning $297, because we're either going to win or lose, right? Multiply by the probability, as you can see. Same thing for the other one, right? The other event is losing, we get -3. That's our outcome if we lose. We're multiplying it by the probability, right? So again, we're taking the outcome, either winning or losing, or the amount that is, and we're multiplying by the probability. So we have 297 times 1 over 150, -3 times 149 over 150. I put a negative here because we're losing. Okay, that's why we have the negative. If you calculate these and add them up, you get -$1. I'm pretty confident that's the right answer. I'm pretty confident that calculation is correct. So what is it saying? This is saying if somehow we were able to play this game over and over and over, or I guess, how do I say this? Have this contest maybe over and over and over and over. Every time you're buying a ticket, they call it, and they keep on doing that over and over. Sometimes you might win, but in the long run, you're going to lose $1. So really, theoretically, this is not something you would want to play. Not a contest you would want to enter, so to say. Although I guess maybe one good interpretation would be, once you win, walk away and don't play anymore. Because in the long run, you're going to lose money. Sometimes you can win, that can happen. It's just that over the long run, if you keep on playing this game, in the long run, take into account sometimes you win, sometimes you lose, and so on. In the long run, you're going to end up losing $1. So, all right. This was okay. So this was a fun example, but now I'm going to change things up a bit. Let's suppose now instead, the winning prize was not $300; it was $453. So they're adding $153 to the winning prize. They threw in the extra 3 especially to account for the purchase of the ticket. So now we're saying the winning prize is more. Now the question you can ask is, okay, should we play the game now? What is the expected value? I got to learn how to spell. That should be WHAT. Let me see if I can fix that quickly. Let me see if I can fix that quickly. There we go. Well, from here is what we would get. So again, the probabilities are still the same. There's only one winning ticket. Every ticket is equally likely, right? The only thing different is the prize money. So if we win, right, we win the $453. We lose the $3 from buying the ticket. So we end up with $450 as our winning prize if we win. And again, that's the probability of that is this, 1 in 150. You could write that as a decimal, but you don't have to. The probability of losing then is still this. And the amount then we would lose would still be $3. But notice now, if we calculate expected value, we actually get something positive. We get 2 cents. Now, 2 cents is not a lot, but what that does imply is this is now the kind of game we should play in the long run. Because in the long run, we should play, that is, because in the long run, we would expect to gain 2 cents. So theoretically, we should play. I mean, I don't know if 2 cents is really enough of a reason to keep on playing. But the fact that we would win overall tells us we should keep playing the game. So before, the prize money wasn't big enough to win, to play the game. Now it is, though, theoretically. Okay. So that's another example. Let me just, oh, sorry, wrong button. Let me just get back to this.